Hi all, it's good to have you here again. The Atlas V rocket has been around launching payloads without a single failure since 2002, and the next one on the list, as I am recording this video, is the Lucy spacecraft, about to visit more asteroids than any mission so far. What makes the ULA's Atlas V rocket so special and what to expect from the launch? That's what this video is about, and it's starting right now. The Atlas V is 58 meters high or 191 feet, but starting from the bottom, the first thing you would see is a Russian Energomash RD-180 engine. Yes, despite having two combustion chambers and two nozzles, it only features a single turbopump and is therefore considered a single engine. It burns RP1 and liquid oxygen and is quite efficient for a first stage motor, almost 8% better than a Falcon 9's Merlin engine at liftoff. Also coming from an old family, the center upper stage has a smaller diameter and uses the extremely efficient RL-10 engine. Manufactured by Aerojet Rocketdyne, the RL-10 engine burns liquid hydrogen and liquid oxygen. The center generally has one RL-10 engine, but sometimes two. On top of that, the fairing, manufactured by the Swiss company RUAG, comes in two sizes, 4 meters or 5.4 meters. The larger size includes the thinner center upper stage inside to avoid aerodynamic issues. The low Earth orbit payload capacity for the Atlas V ranges from 9.8 tons to 20 tons. The tanks are not full in smaller versions, but when the tanks are indeed full, the rocket is then too heavy to lift off. That's why solid rocket boosters or SRBs made by Northrop Grumman are added to help with liftoff. With so many options, the naming scheme helps understand which version features what option with the 3-digit codes. The first one is the fairing size, 4 or 5 meters wide, or an N for the Starliner that doesn't require a fairing. The second one is a number of SRBs ranging from 0 to 5, and the last digit is a number of engines on the center upper stage, generally 1, but 2 for Starliner. The price range varies accordingly from $109 million to $153 million. Out of the 20 possible combinations, only 10 have flown, the 401 being the most popular. There even was a heavy version on the drawing board with 3 cores, able to send 30 tons toward low Earth orbit, but it was abandoned in 2006. If you compare the Atlas V to a reusable Falcon 9 rocket, an Atlas V 531 with 3 SRBs is needed to match the payload delivered to low Earth orbit, and it costs twice as much as a Falcon 9. But if you aim at a geostationary transfer orbit, an Atlas V 411 with a single SRB can launch the same payload. That's because of the high performance of the center upper stage compared to that of the Falcon 9. To launch the Lucy spacecraft weighing a little more than 1.5 tons and needing a C3 of 28.6 km² per second squared, a Falcon Heavy would have been needed, whereas the little Atlas V 401 is perfectly capable of launching it. But ULA has a price problem. Even the mighty Falcon Heavy is cheaper than the small Atlas V 401. Although ULA is not that far behind, the rocket itself might be expensive, but the total cost of the launch is much closer between the two companies, and in fact, ULA can be the cheapest option sometimes. In the recent GEOSU award won by SpaceX with a $152.5 million bill, ULA's bid was $140 million, but had to withdraw because the Atlas V is retiring in favor of Vulcan. Be a little honest here, did you think ULA could be cheaper than SpaceX sometimes? Tell me in the comments below. I for one did not expect that. But ULA's main value is their perfect scorecard with bullseye precision when it comes to launches. They also have a trade secret with one steering, and I will talk about it in a few seconds. But first, let's look at a launch. A launch doesn't start with engine ignition, but rather 12 hours before when the countdown is started. At that moment, the non-essential personnel clear the pad, and the launch operations begin with the Atlas rocket beginning to move towards the launch pad. 3.5 hours later, the rocket is secured in place, and preparations begin for fueling. Those preparations take a long time, and then, 2 hours before the flight, the countdown is halted for about 30 minutes. Enough for the launch manager to poll teams if they are go or no-go for tanking. If everyone is go, then the countdown resumes with chill-down of tanks and transfer lines. 103 minutes before launch, liquid oxygen tanking starts on the center upper stage. 90 minutes before launch, liquid oxygen and RP1 tanking start on the Atlas first stage. 85 minutes before launch, liquid hydrogen tanking starts on the center upper stage. 60 minutes before launch, the center RL-10 engines begin chill down, Some liquid oxygen is poured into the engine to chill it. If the engine is not cold enough when the engine is lit, the liquid oxygen and hydrogen could start boiling and cavitation would occur. The tanking will last until 4 minutes before launch, when the launch manager starts the last go-no-go poll while holding the countdown. If everyone is go, the spacecraft transfers to internal power and the computers take control of the launch sequence, monitoring tank pressure and topping off the tanks up until 110 seconds before launch. The launch control system takes over during the last 90 seconds of the countdown, up until 0, ignition and liftoff of the Atlas V. At liftoff, both the RD-180 main engine and eventual boosters are ignited and will remain so for 95 seconds. After that, the boosters are simply ditched and will crash into the ocean. On some missions, they are kept for a little while to ensure they crash in a specific area cleared of any boat or plane. Depending on the mission, and therefore on the levels of fuel inside it at liftoff, the first stage can remain active for up to 253 seconds total. Compared to Falcon 9's first stage, 160 seconds, that's way longer. This is both because the Falcon 9's first stage needs to come back intact and therefore stop before going too fast, and also because the center upper stage engine is really weak, with a low thrust-to-weight ratio. Since the RL-10 engine on the Atlas needs to burn for a longer time than the Merlin vacuum engine on the Falcon 9, the first stage needs to send it higher. So the center upper stage is basically thrown on an arc and is desperately trying its best to finalize its orbit before falling back down to Earth. Of course, this minor inconvenience is offset by its outstanding efficiency. But let's go back to that RAN steering I talked to you about before. ULA's secret ingredient when it comes to launching payload is called RAN steering. Almost all rockets do steer to reach their intended target orbit, but that's on the roll angle required for liftoff, or the pitch angle to follow the intended trajectory. Some, like the Falcon 9 when launching on a polar orbit from Florida, do steer on the yaw axis to avoid flying over populated areas. That's impressive, but is only used in a reference to a trajectory plotted in advance. RAN means right ascension of the ascending node. This refers to the ascending node, the point in your target orbit when the spacecraft crosses the Earth's equator going upwards, or north. But the right ascension is its position relative to a fixed referential, not relative to a rotating Earth. This notion is used to rendezvous with another spacecraft, mostly the ISS these days, or to replace a specific observation satellite, for instance, when the Landsat 9 was launched to replace the Landsat 7 satellite on the same orbit. Of course, when it comes to observation satellites, the military launches a lot of them, and the target orbit always specifies a RAN to ensure good coverage of the Earth. A specific RAN on a heliosynchronous observation satellite means it will pass each day at a specific time. If you target a specific RAN, then you have a launch window each day, but this window is instantaneous. You either launch on time or have to wait 24 hours. But ULA's RAN steering allows the rocket to still reach a specific RAN, even if it's launched sometime before or after the optimal launch time. This widens the launch window up to 2 hours instead of a specific time. Hey, if you found this video useful so far, please click the like button as it will help it reach more people. The Atlas V needs between 4 and 15 minutes to recycle for a new launch attempt depending on when the abort occurs, and therefore there is a good chance the satellite can be launched on a specific day. ULA's rockets are the only ones able to use this technique. It is successfully implemented on the Atlas V and the Delta IV, and Vulcan will use it too. SpaceX's Falcon 9 do not use this technique, but since they are using superchilled liquid oxygen to increase performance, the rocket needs a lot of time, at least 1 hour, to recycle in case of an abort. Therefore, RAN steering would not be of any use in that case. But for many SpaceX flights, though, the added performance of superchilled liquid oxygen is not needed, and maybe they should look into it in the future. It will probably never happen though. RAN steering uses a performance margin, basically fuel that would not have been used anyways, but Elon Musk previously said he wants to get rid of as much unused fuel as possible to increase performance. Anyways, RAN steering is not always used at its full capacity. It can in theory start right after Mark Q, sometimes with RBs still attached, but it will only be used during the second center burn for Lucy to reduce range tracking analysis and ease the coordination of downrange assets. That's because the flight path can change significantly based on the amplitude of RAN steering used. RAN steering was also supposed to be used when launching Starliner towards the ISS, but since it would have meant a wider rescue area in case of an abort, it was decided not to use it, and Starliner has an immediate launch window instead. But the Cygnus OS-6 cargo mission in 2016 probably was saved by RAN steering and the propellant margins left in the center upper stage when the first stage shut down early. Anyway, that's what you can expect from Lucy's launch in a few days. If you want more information about this exceptional mission, then you have to watch this video explaining in detail how the Lucy spacecraft will navigate towards its multiple targets and how it will study them, bringing us a new understanding of the early days of the solar system.